Hey everybody, it's Mr. N here, and this is section 3-1, chapter 3, section 1, the lesson that we're going to do, but this lesson is on pairs of lines and angles. Most of you have already been taught this, but it's great review, so let's take a look at it. And over here, we know what parallel lines are. Parallel lines are coplanar lines that do not intersect. And this is only true in Euclidean geometry. Just be aware of that. In Euclidean geometry, parallel lines do not intersect, but other types of geometry, and we've talked about this. There are other types of geometry. I can have a sphere and do the geometry on a sphere. That's real world. That's what we're in. We live in a sphere. And if we do parallel lines in a sphere, they will intersect. So we can say by nature parallel lines don't even exist in a sphere. Let me explain to you. Now, the Earth has curvature. If you draw a straight line and keep drawing it out, it's going to start curving due to the curvature of the Earth. So we don't live in a flat plane. We live in a sphere. And geometry will be different on a sphere. Now, to get exact with this, suppose I did have a sphere here. Lines in a sphere are defined as going through a great circle. In other words, it has to go through the middle like this. So any line I draw kind of goes through the middle like that. Okay? And so by nature, none of these will be parallel because they will intersect at the poles over here. So they won't be parallel because they will always intersect at the poles. So imagine I take an orange and I just slice it down the middle, then slice it again. But each time I have to go through that middle. And those are the lines I'm creating, and they will intersect. So really in a sphere, parallel lines will intersect because there's no such thing as parallel lines in a sphere. But in any case, we're doing Euclidean. So this is all based on a flat plane. So on a flat plane, we can have parallel lines. They're coplanar. They do not intersect. We can have perpendicular lines. Perpendicular lines make a right angle. In fact, this also goes into how they've been able to determine space is flat. They've been able to, as far out as they can go, they've been able to make a triangle, and the sides add up to be 180. And so that's kind of interesting too, because as far out as they can see, there's no curvature to it. Its space is pretty flat. But yet we are on a round sphere. It's all bizarre. It really is. But in any case, let's look at skew lines. These are non-coplanar lines that do not intersect and are not parallel. So we have parallel lines, we have perpendicular lines. You can look at all the examples here. Skew lines, coplanar, don't intersect. Well, how does that happen? Well, now you have to think three-dimensional because it's non-coplanar. So if I think three-dimensional, EF right here, this one. So if EF goes across like this, and then HW down here, well, those will never intersect if you're looking at three-dimensional like that. So those are skew. And then parallel planes are going to be planes that don't intersect. So planes that are parallel to each other. So this top part right here, ABFE, and the bottom one down here, these will be parallel planes, just like the sides. This side over here, that side, and the front and the back. Then we've got the parallel postulate. This is crazy, and I'll explain why in a minute, but let's go over it. It says, if there is a line and a point not on the line, then there is exactly one line through the point parallel to the given line. All right, so let's get crazy with this, and let me explain to you. You got to get excited about math. Come on, this is crazy. We are, as I said up above, we are learning Euclidean geometry. And this is after a guy by the name of Euclid, of course. And Euclid came up with all these postulates for geometry. He said, okay, these are all the things that must happen in geometry for geometry to work, just like we have all these other postulates in math for math to work. Now, he came up with the parallel postulate. This was his fifth postulate. He had many others, But it was this fifth postulate that drew a lot of criticism from mathematicians, but they couldn't explain why. So basically, he's saying this. If you have some sort of line here, okay, and a point not on the line. So I've got line L and point P sitting out here. I can only draw one line parallel to L through P. That makes sense. Yeah, you can only draw one line parallel to it. And so, even though it made sense, it's still, some people, it did not sit well for them. If you really think about this, it doesn't sit well with you. But you got to remember, Euclid was around 300 BC. And so he came up with this. He came up with his book called Euclid's Elements, which was pretty much the first geometry book. And this was the fifth postulate in there. And it was just accepted. But it never sat well with mathematicians, but nobody can prove why. Until around 1830s, in that, this is AD now, so it took that long before two guys independent of each other, one of them was named Bolya and the other one was Lobachevsky, they finally proved that this does not work. It only works for Euclidean geometry for this fifth postulate. If you are talking about any other type of geometry, such as hyperbolic, basically you could do geometry on any type of surface, right? We do it on a flat plane, flat surface, but the Earth is round. There's other types of surfaces out there. If you do geometry on another type of surface, the fifth postulate is not true and does not hold. So you would be able to draw possibly more than one, or you wouldn't be able to draw any. So depending on the situation. So the fifth postulate is the parallel postulate. It's really important, and it only works, though, in Euclidean geometry. Same with this next one, the perpendicular postulate. This one says if I have line L here and point P, I can only draw one line perpendicular to it. So those are just some pretty interesting math things. Yes, I'm a math geek. Mr. N is a math nerd, and he's proud of it. So you may not find it exciting, but I do. So anyway, here we go. Let's take a look at some other definitions. Again, these are things that you may have been taught, but we're going to talk about them. And today we're going to keep these lines not parallel. So let's take a look. A transversal. Actually, let's talk about this one real quick. Here's a theorem. If you have two parallel planes cut by a third plane, then the lines of intersection are parallel. So this kind of goes along with that, but with planes. So if you've got two parallel planes, and then they are cut by a third plane, then the lines of intersection formed will be parallel. Okay, so basically think of your ceiling and your floor. They are parallel. They're going to intersect your wall, and so the lines that intersect your wall will be parallel to each other. All right, so now let's talk about these words right here, this terminology. First of all, this thing is called a transversal. So if I have two lines, you can have a line that intersects both these. So you can have two or more lines. I could draw a third, a fourth, a fifth. This would be the transversal, this red line to all of them. So a line that intersects two or more coplanar lines in different points. So this red line is called the transversal. To the two black lines that you see. Then you've got alternate interior angles. These are two non-adjacent interior angles on the opposite sides of the transversal. So now I'm going to do something. I'm going to number everything. I'm going to number these angles 1, 2, 3, 4, 5, 6, 7, and 8. And let me explain to you what alternate interior angles are. Alternate interior angles would be like 3 and 6. So if I make a Z, the insides of the Z, let me make that Z again for you. Let me use a different pointer right now. So here's the Z, follow it along, there's the Z. The insides of the Z are called the alternate interior angles. Now, you can make the Z backwards. If the whole thing was rotated around, it doesn't matter. As long as you can make a Z. So look, I can make a Z this way. In this direction, I made a Z. The insides of this Z are 4 and 5. That's the insides of the Z. We can call these alternate interior angles. Alternate exterior. The easiest way to do alternate exterior is to first find the alternate interiors and then go vertical. So 3 and 6 are alternate interior, go vertical. 2, go vertical. 7, 2 and 7 are alternate exterior. So find your alternate interiors and go vertical. Over here, 3 and 6 are alternate interior. Go vertical. Oh, sorry, I did that one. 4 and 5 are alternate interiors. Go vertical. So 1 and 8 would be the alternate exteriors. So let me list these down for you. The alternate interiors would be 3 and 6, angle 3 and angle 6, angle 4 and angle 5. So that means the alternate exterior would be angle 2 and angle 7, and then angle 1 and angle 8. All right. Same side interior. Some books will call this consecutive interior. So same side interior, think of it as you have your transversal, and then you're going to go on the same side and on the inside of that transversal. So right here is my transversal. Okay, I'm going to go to the left and I'm going to go to the inside. So 3 and 5. These are two interior angles on the same side of the transversal. So same side and on the inside, 3 and 5. So this would be angle 3 and angle 5. Well, you got the other side too now. So now we can go, here's the transversal, 4 and 6 are on that same side and they're on the inside. So angle 4 and 6. You can also do same side exterior. I'll write it down here, same side exterior. Well, okay, same situation. I'm going to go on the same side, to the left of this transversal, but on the outsides now, on the exteriors, 1 and 7. Oops. Let's use the red one again. Angle 1 and angle 7. Just like on the other one, angle 2 and angle 8. Just like I said on this other side. I'm going to go to the right of the transversal and on the outsides, 2 and 8. All right, let's take a look at the next page we have. Then we've got corresponding angles. Your author likes to call this one a theorem. Corresponding angles is the only one out of these that is a postulate. It must be a postulate to work, okay? Again, the author of Big Ideas, I'm not a fan of his with this calling it a theorem. Every other book will refer to it as a postulate. So, two angles in corresponding positions relative to their line. So let's take a look at the example that I had above. I'm going to just redraw it here. It'll be easier if I just redraw it. We had this line, we had this line, we had our red transversal, and then I number these 1, 2, 3, 4, 5, 6, 7, 8. Very similar to the picture that they have here. So corresponding would be 1 and 5. Now, corresponding, I say a postulate. Right now, just to clarify it, right now we're just talking about what corresponding is. When we start putting this into theorems and postulate, always know that corresponding will be a postulate. Right now, I haven't said anything to show you that it is a postulate, but in the next lesson we will. Okay, so I just wanted to clarify that. But again, looking over here, 1 and 5, they correspond to each other because they're both to the left of the transversal and above each line. Left and above, 1 and 5. Right and above, 2 and 6. So corresponding would be angle 1. Let's change back to red. Angle 1 and angle 5. Angle 2 and angle 6. Okay, what about to the left and below? That would be angle 3 and angle 7. What about to the right and below? That would be angle 4 and angle 8. So those could be all corresponding. And this chart, again, just talks about everything I just talked about in the previous examples, and they relate it to here. So it's just the same exact thing that I did, but here it is all typed out nice for you instead of my chicken scratch. All right. Most of this was terminology and identifying things, so I don't have any additional examples for you because it would just be us identifying them, and we're going to do that in class. So in class, we'll work on the student journal, and most of it will be identifying which of these angles we're talking about. So thanks for watching. Make sure you hit that like and subscribe button, and I will see you guys in the next video.